All right, Advanced Math A, here we go. We've got lesson 8.1.6, multiple representations of exponential functions. So in this section, we're not going to do anything super new. What we're just going to look at is looking at exponential functions as a situation, as a graph, as an equation, as a table, and kind of just jump from one of those to another. So we're just going to go between those four different formats of graph, equation, table, situation. First problem just says, what kind of situation could fit this data? All right, so I got 16,000 here. Years are going by. What could this be? Well, it's got to be something that decreases, starts at a big number like 16, and it happens over years. So I don't know. Maybe this is a population of some kind of endangered species or something like that. Or with $16,000, it could be something like a car. And we've talked about in class that a car decreases in value over time. So if we would make this into a situation, we could see here that it went from 16,000 down to 14,000. So it's lost quite a bit there. So if we want to see that rate of decrease, what we could do is say, okay, what's 14,000 divided by 16,000? So that's a decrease of 0.875. Okay, so that's the multiplier, which makes sense since it's going downhill. Our multiplier should be less than 1. So let's say that the situation is we bought a car for 16,000. Now here's the interesting thing. This 0.875, that's how much we're keeping every single year. That's not how much we're losing every single year. So usually we would think of this in terms of how much we're losing every year. So what we would do is we'd say 1 minus r equals 0.875. So r is the rate that it's decaying by, which would be, what's that, 12.5? Would be 0.125, yeah, that looks right. So we bought a car for 16,000 and its value decreased by 12.5% every year. Okay, there's the situation there. Next one, we've got 180 times 1.22 to the t power. All right, so what could be 180? And then we add 22% to it. So this is going to be an increasing function. So it's going to be increasing by 22%. Let's say that the number of let's say trout in a lake is 180, and they will increase by 22% each year. So we can see here that our starting value is 180, so that's the trout that we have right now, and we expect it to increase by 22%. So why is it 1.22? Because when we have an increasing function where we have growth, it's 1 plus the rate of growth. So the rate of growth is 0.22 or 22%. Okay, here we've got a table, and this table starts at 1980, and there's 226 million. And then it looks like it says we're going to multiply by 1.02 each year. And we're going to get it down. Wow, it's going to go up to 1 billion people. I'm probably saying people. I just came up with people because that made sense to me. So maybe this is a population of some country. Let's say the country of Holcomlandia. That sounds like a good country. So we'll say that the population of Holcomlandia, it's a really cool place. They do a lot of math there. In 1980, was I can't spell 226 million and increased by 2% each year. So no right way or wrong way to do this. We just had to come up with some kind of situation that could match what we've seen there. So we see that with the graph, we can find our rate of growth or decay by taking 2 points and dividing them to find that rate. In a equation, we've got our rate inside here in our b value. And in a graph, we've got our starting value here, and then by seeing what we're multiplying by each time, we can find our rate of growth there. Next. This is where I got the trout from. I was thinking, where did I come up with trout on that problem? There you go. It's because of this problem. I read it earlier. All right, so we got a virus has invaded Leticia's favorite mountain fishing lake. Currently, there are an estimated 1,800 trout in the lake, and the Fish and Game Department has determined that the rate of fish deaths will be 1/3 of the population per week if untreated. All right, so we got a fish kill going on here. This is not good. So we want to sketch the graph over several weeks. Okay, so we're losing 1/3 every week, which means we're keeping 2/3 every week. So week 0 would be before the virus is attacking over them. So then this would be the first week, second week, third week, fourth week, fifth week, so on and so forth. So this is the number of weeks since the virus started attacking. And this will be the number of trout. Because we've got 1,800 on this one, I should probably be by 200 maybe. This will be 200, 400, 6, 8, 1,000, 1,200. Should have just skipped every one. 1,600 and 1,800. All right, so there's our graph. So now we know that our starting amount is 1,800. And then we're going to divide by 3 every week. So we're going to divide by 3. So 1,800 divided by 3 is 600. 600 divided by 3 is 200. 200 divided by 3 is, what's that, 132, blah, 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 blah. So 132, we'll call it right about there. And then we're dividing by 3 each week. It's going to get closer and closer to 0 there. All right, theoretically, ill the trout, I think that's supposed to say will the trout ever completely disappear? Theoretically. Okay, in actuality, things are different from theoretical. This one, we would say no. Theoretically, because there is an asymptote here where we can never get to 0 trout. So theoretically, that's a what-if situation. This is based on the equation. Based on the equation, no, we'll never get down to 0. Now, in real life, we probably would get down to 0 because at some point, the virus is going to affect so many trout that they can't keep up their population. But theoretically, no, because of the asymptote. No, because the asymptote won't let us get to 0 fish. So we've got that asymptote that's keeping us to go from the y value getting to 0. Next, suppose the annual fees for attending a public university were $7,000 in 2010, and the annual cost increase is shown on this graph over here. We're supposed to write an equation to model this situation. So this would be year 2010, and that's going to be our year 0, and that's our y-intercept, so that's our a value. To find our b value, we have moved over on the x-axis by 1, and we've increased by 700. So this would be 7,700 divided by 7,000. So if I do 7,700 and divide by 7,000, we get 1.1. So our b value is 1.1. So our equation to model this situation would be y equals 7,000 times 1.1 to the x power. So what is this saying? It's saying that public education annual fees are growing by 10% per year. And that's what this is saying. Use the model to predict the cost of attending a public university in 5 years. So that would mean that our x value is going to be 5. So we would say y equals 7,000, and then we're going to do 1.1 to the 5th power. All right, let's see how much it's going to cost. 1.1 to the 5th power is that number, and then I'm going to multiply by 7,000. And we get $11,273.57. So in 5 years, we went from 7,000 to 11,273.57. Next question. What is the cost in the year 2000, assuming the rate of increase was the same during the time period from 2000 to 2010? Well, this is 2010 right here. So 2000 would have been to the negative 10 power because we are going backwards in time. So we're going to go where it's going to get smaller here. So we're going to do y equals 7,000 times 1.1 to the negative 10 power. So we're going to do 1.1 to the negative, hit the negative button down here, negative 10 power. I get that number, and then I multiply by 7,000. 2698.80, we're going to call it. So 2698.80. So this is approximately 2698.80. So going backwards in time, we're going to use negative exponents. What is the predicted cost for 2012? That would be y equals 7,000 times 1.1 to the 2nd power. So that's one way we could do it. Or I could just take 7,700 and multiply by 1.1. I'm going to get the same answer. So 1.1 to the 2nd power gives me times 7,000, gives me 8,470. Now, if I took 7,700 and multiply by 1.1, I get the same exact answer of 8,470. All right. Now, in 2012, the actual cost, or the annual cost, was actually 8,244. So our equation that we've written here is a prediction. This is the actual. So this is actually what happened. So why is this number different? Because there was a residual. Remember residuals? Yeah, here they are again. So what we do with residuals is we do actual minus the predicted. So if I do 8,244 minus 8,470, we get a negative residual. The residual is negative 226. Thank you, Bill. don't you do, okay, it's 2:45. Good. They're not going to have any trails yet. All right, so I've got a negative residual. Seriously, they're going to do it. I'm going to pause. Okay, they stopped playing that song. Thank goodness. So this negative residual means that the model, our equation, wasn't completely accurate to predict the future. So what this means is our model, our actual values, was lower than what the model predicted. So the cost of education did not grow as fast as we thought it would way back in 2010. So that's what that means. All right, next page. Okay, so this one says draw a sketch of each equation without making a table first. So a sketch does not have to be super accurate. It's just a general idea of what's happening. So let's just make a quick sketch here. I know my y-intercept is 5, so 1, 2, 3, 4, 5. There's my first point. I'm going to multiply by 3, so 1, 2, 3, 4, 10, 1, 2, 3, 4, 15. So the next point would be here, and going backwards, I would be dividing it by 3. So this would be 1.6 repeating, and then it gets smaller going the other way. So this would just be a sketch. Ooh, that wasn't very good. There you go, we sketched it. Next one, we've got the y-intercept at 10, but this time we've got a b value of 1/2. So what does that mean? It means we should have a decreasing function on this one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say 10's there. And then it's going to cut in half each time. So the next one would be at 5, the next one would be at 2.5, and the next one would be 1.25, and then the next one would be lower, and so on and so forth. Now going the other direction, I would be doubling the amount. So the other number over here would be negative 120. So there's my sketch of the graph. Again, these are sketches. They don't have to be perfect. But we do know that we would have an asymptote right here on the x-axis. Next one, we've got y equals 1/10 times 5 to the x power. So for this one, oops. My pen's running out of ink. Makes me sad. I'll switch to this color. All right, so if we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1/10 would be way down here. And then we do 5 to the first. 5 times 1/10 would be 1/2. And then I'd multiply by 5. 1/2 times 5 is 2.5. So it'd be about here. And then we keep on multiplying by 5. So the next one, if I take 2.5 and multiply by 5, I end up with 12.5. So the next point along our lines, I think that was 10, so it'd be somewhere up here-ish. Going backwards, I'd divide it by 5 and it'd get even closer to our asymptote there. So we notice that with the bigger numbers here as our b values, we get steeper. When we have a number between 0 and 1, we get a decreasing function right there. Last part, we're going to write equations and solve for each of the following. We've got a 100-gram sample of radioactive isotope. It decays at a rate of 6% every week. How much will be left after 1 year? So we're supposed to write an equation and solve. So our equation for this would be y equal, we're starting with 100. Our decay is 6%, but this is how much we're losing. We want to know how much we're keeping, so we're going to do 1 minus 0.06. 1 minus 6%, which is 0.94. So we get 0.94 here. If we're losing 6%, we're keeping 94%. So that's what this is keeping track of, is how much we're keeping. And then years would go, or weeks, because this is every week, weeks would go up here. So they want to know how much is going to be left after 1 year. Well, in every year there's 52 weeks. I think it's 52. It's been a long day. I can't remember numbers. 0.94 to the 52 power. Okay, so we'd take out our calculators and we would take 0.94, raise it to the 52nd power, and then multiply it by 100. And it looks like there's going to be about 4 grams left. So approximately 4 grams after 52 weeks. Next one. The math club is fast becoming one of the most popular clubs on campus, of course. That happens all the time. Each year, the club's enrollment increases by 30%. So this is a growth situation. If the club has 45 members this year, how many should it expect in 5 years? Okay, so it has 45. That's my A value. And then this is my R value. And since it's an increase, I'm going to do 1 plus R for my B value. So I got Y equals, the A value is 45. And our multiplier, or our B value, will be 1 plus 30%, or 1.3. And then X for the number of years. And then to solve the problem, we want to know what's going to happen in 5 years. So we're going to say Y equals 45 times 1.3 to the 5th power. All right, so I'm going to take 1.3, take it to the 5th power, and then multiply by the 45 students. And I get 167.08. I'm not going to have 0.08 students, so let's just call this 167 students. Math club is booming, as it should. All right, next one, part C. Barbara made a bad investment. Wah, 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 wah. So rather than earning interest, her money is decreasing in value. Okay, so this is going downhill. This is decay. Her money is decreasing by a value of 11%. So that's my R, and since it's decreasing, we should do 1 minus R, because this is how much we're losing. But remember, when we do exponential functions and they're decreasing, we're keeping track of how much we're keeping, not losing. Okay, so after 1 week, she's down to 142.4. Now that is not our A value. We need to find our A value. So far, I know that this is Y equals 1 minus 0.11 is 0.89. But I don't have my A. So normally to go forward, I multiply by 0.89. So to go backwards and find the 0 value over here, I'm going to take 142.4 and divide by 0.89. So 142.4 divided by 0.89. So that means that she started off with $160. So that's our 0 value there, or our A value, because it's the y-intercept, that's the starting. So that's at week 0. That's before she made the investment. She has $160. Multiply that by 0.89, and that's why after 1 week we got 142.4. Okay, so how much money did she start with? We already solved that. That was 160. That's the A value. How many weeks will go by until she has only half of her original investment? That's interesting. We're going to have to find that out somehow without using logarithms, because that would be crazy. So what we're going to do for this one is we're just going to start plugging in some numbers and see when we get close. So let's take 0.89 and take it to the 4th power. That's 0.62. Now to get to half, we would need to be to 0.5. So let's go a little bit more. 0.89 to the 6th power. 0.49. Let's do 0.89 to the 5th. All right, so it looks like 6th power is the best one, because that gets me really close to 0.5, which would be half. So let's show that. So we do Y equals 160 times 0.89 to the 6th power. So if I do clear. There you go. All right, so if I do 0.89 to the 6th power, and I multiply by 160, yeah, I get 79.51, which is close to a half. So it looks like, there's my answer, about 6 weeks. All right, last one. Thanks for sticking with me so far. Larry bought $285 worth of music using his credit card. That's a bad choice, Larry. And now he cannot afford to pay off his debt. That's what makes it a bad choice, Larry. If the credit card company charges him 18% annual interest compounded monthly, how much will he owe after 1 year? You might think an 18%, that's a lot. No, that's not a lot. Credit card companies charge a lot. So you always want to pay off your credit card because the $285 worth of music that you bought is going to end up costing you a lot more with 18% compounded annual or compounded monthly. So our starting amount for poor Larry, who makes bad decisions, we're going to do 1 plus the 18%, but then that 18% is going to be split up monthly because they're compounding it monthly. So I'm going to divide that 18% by 12. And then X is going to be the years because it's annual interest. But since I'm compounding monthly, that means each year I have 12 time periods. So I multiply by 12 up there. In this case, we want to know how much he's going to owe after 1 year. So X should be 1. All right, let's make this look a little bit nicer. Let's take 0.18 and divide by 12. It comes out to 0.015. So that's 1.5% per month is what they're charging us. It's 18% for a whole year, and what they're going to do is 1.5% per month. And then it's going to be 1 year, so this is going to be 12 time periods that we're going to be dealing with here. So the 0.015 means each month they're going to charge 1.5%. And if you add up 1.5% 12 times, that comes out to the total 18%. So they've just taken up that 18%, sliced it up, and they made it into individual months. So there's 12 months here. All right, so 1.015 to the 12th power, because there's 12 months in the year. And then we're going to multiply by 285. Oh, what did I do? 1.015 to the 12th power, and then multiply, I forgot to hit the multiply button, 285. All right, congratulations. That music that you wanted so badly and just had to have that cost you $285 now has cost you $340.75. Was it worth it, Larry? Was it? Was it worth paying that much more for it? No, it was not, Larry. Bad choices. All right, so that's all we got for you today. Math hard. See you later. Bye.